double price. Go MBS.
Times 2, times 4, times 8.
Is it your investment plan to go MBS?
Yeah. Also next time I also strike 4D also sure. Times 2, times 4, times 8.
No matter you all can win faster.
You say you put inside the 3, you play the dice, 3 the same digit, 180 times. For example, 1 M with 180 M already. Storage.
1 hour is possible, definitely.
You wish the dice like.
But total how much I don't know, I never tried it.
Somehow you just 3 of it there.
Yours is how many goals?
So not mine, this is roughly
16 already. I just installed 8 stuff in.
For mine 8 around 1
stuck
hour
in traffic jam.
1 hour die.
1 hour too much.
Recording going on.
Plus photo.
Not recording.
Rafi's one.
Oh, Rafi's son.
He's so late. He's late.
Oh, traffic jam.
Yeah, traffic jam.
You come out late, I think.
Doing something last night.
Outing.
Yeah.
So I said go and buy all the beer.
Also, NCT Tottenham all lose, so Liverpool also lose. Liverpool used to win, but NCT and
Yeah, the one.
Man U also used to win.
bad luck.
Too ambitious.
Not bad. Not bad.
If it is our team, confirm lose one.
I mean, you got Liverpool. What's he driving? What are you doing for business plan? What are you doing for business plan? Your plan,
You saw me already.
done already?
Business. Yeah.
That's very early.
Business proposal. Yeah, business
So fast then what your lead? So now is the presentation phase.
This Wednesday.
This is the presentation.
Later we meet, then do presentation.
About what? What's the business about?
But this kind of lock, this kind of lock, like you don't need to use keys or what.
Okay.
Let's use card.
No card. Handphone.
Handphone open the door.
Okay. Before we start this week's tutorial, I would just like to go back to a question we had from last week's tutorial, because there was a mistake in the solution presented. Okay, so this is the answer to last week's question 1b. Remember that for question 1b, we could issue 2 instructions in the same cycle, and then we were asked to work out how many cycles it would take to execute the 2 iterations of the loop. So, as somebody pointed out last week, okay, we have these data dependencies, and if there's a data dependency, then we have to wait for the value to be written back before we can use it. So here we write back f0 in cycle 9, and we have to wait until cycle 10 before we can use it. But when we're waiting for the multiply unit, here we have a multiply instruction which executes from cycles 4 to 8, and then we write back in cycle 9. So here we're waiting for the multiply unit, but we can use the multiply unit in the same cycle that we're writing back. Okay, because we finished executing the multiply, so even though we're writing back in cycle 9, we can start this multiply also in cycle 9. Okay, so there's a difference when you're waiting for a data dependency and when you're waiting for a particular unit to become available. So when you're waiting for a unit to become available, again, another example here, we're waiting for the integer unit, but the integer unit, we write back in 10, we can start to use the integer unit in 10. Okay, so the correct solution for last week then...
Right band, use it from there.
Yeah.
So it's in.
That's what I'm saying.
If you count up the total number of cycles, the last cycle is 18, so therefore the time per iteration is 18 over 2, which is 9, rather than what we had last time, which was 9.5. Okay, are there any questions on that? Okay, so let's go on to this week's tutorial then. So, okay, so this week's tutorial is about memory hierarchy, and in particular the use of cache memory. So remember that by using cache memory, we can access the cache memory much more quickly than we can access the main memory, so we can speed up the execution of the program by using cache. So the first two questions really ask us to work out how much benefit we can get from using cache memory. So we're told for the first question that we have an array of 10,000 integers, and we suppose that we have a cache, a data cache, which can hold 100 integers. Okay, so we have 100 locations for integers in our data cache. And we're also told that if we have a cache hit, so if the data is already in the cache, then we can access it with just one CPU cycle. However, if the data is not in the cache, then we have a penalty, called a miss penalty. So if we have a cache miss, we have to pay a penalty of 30 CPU cycles in order to transfer the data from the main memory into the cache memory. So the first example says that suppose we access this array sequentially, and suppose if we do this, the hit rate is 99%. What will be the mean access time? So by the mean access time, we mean the average access time taking into account those locations which are cache hits and the data which is a cache miss. So how do we work this out? Well, we have a formula for this. If we have a cache hit, then the access time will be the hit time, the time for a hit. If we have a cache miss, we have to pay the penalty. And then we also need to access the cache data as well. So if we have a cache miss, we have a time which is t hit plus the t miss penalty. So therefore, if you know the hit rate, you can work out what the mean access time will be. The mean access time will be the hit time plus 1 minus h, where h is the hit rate, times the miss penalty time. So, for this particular example, where we have a hit time of 1 CPU cycle, a miss penalty of 30, and a hit rate of 99%, can anybody tell me what will be the mean access time in terms of cycles? If you use this formula, what will you get?
1.3?
1.3, yes. Okay, so just put the numbers into the formula. The hit time is 1 cycle. The hit ratio is 99%. So we have 1 minus the hit ratio, and then the CPU, the miss penalty is 30 CPU cycles. So if you work that out, you get 1.3. Okay? Slightly different example. Suppose we access this array of data in a different way, and now we're told that the hit rate is 30%. What will we get now for the mean access time? Again, use the same formula. What do we get? So in terms of 22. Okay, so again, again, use the same formula. Hit rate is 1. The hit time is 1. The hit rate is 30%, or 0.3. 1 minus 0.3 times 30, and altogether we get 22. Okay, so far? Okay, so let's go on to the next example then. In this case, we're told that the array will be accessed in a random fashion. So instead of accessing the array in a particular order, each time we just use a random number to work out which location we access. So again, we've asked what the mean access time is. In order to calculate that, we have to work out what the hit ratio will be. So if we access this array in a random fashion, what will the hit ratio be? Okay, we have an array of 10,000 integers, and we have a cache of 100, and we do it in a random fashion. What will the hit ratio be? In terms of as a percentage, anybody tell me? 1%. Okay, because we have 10,000 integers in our array, and we have 100 integers in our cache. So if we're doing this randomly, the chances of the data we want being in the cache will be 100 divided by 10,000, which is 1%. Okay, so we've worked out the hit ratio, all we have to do now is to put this into the formula. So again, the same as before, 1 for the hit time, plus 1 minus the hit rate. Hit rate is 0.01, multiplied by the miss penalty, 30, and that comes out as 30.7. So, the last part of the question asks us, what conclusions can we draw from this? Okay, so in the first part, in part A, we had a mean access time of 1.3 CPU cycles. In the second part, we had 22 CPU cycles. Here we have 13.7 CPU cycles as the mean access time. What conclusions can we draw?
The higher the hit rate, the lower the CPU cycle.
Yeah, okay, so
This is the
the higher the hit rate, the lower the CPU time. And also, having a high hit rate is going to be very important for good performance. Okay, if you want to access the memory efficiently, you should try to ensure that you have a high hit rate. Okay, that's question number 1. Any questions on question number 1?
see the shack face.
Okay, so let's go on to question number 2 then. Again, we're talking about the use of cache memory here. But in this case, we're talking about the execution time. So, first of all, we're told to assume that the CPI, or the cycles per instruction, for a particular computer is 1. Okay, so this computer takes 1 cycle per instruction when all of the memory accesses are cache hits. We're told also that this program will access data, but the only data accesses are the load and store instructions, and they take 40% of all of the instructions executed. And we're told also to assume that the miss rate for either instructions or data accesses is 5%. And if we do have a cache miss, we have to pay a penalty for 25 clock cycles. And then we're asked, how much faster would this machine be if all of the memory accesses were all hits? Okay, so again, we have a formula for this. So we can calculate the total execution time as being the number of CPU clock cycles. So those are the clock cycles to execute the instructions, and also included in the execution time are the memory stall cycles, where we have to pay a penalty for the cache miss, and if you want it in seconds, then you can multiply that by the clock cycle time. And then we have some more formula for the memory stall cycles. So the total number of memory stall cycles will be the number of cache misses times the miss penalty, the time you have to pay if there's a miss. So if IC is the instruction count, then the number of cache misses will be the instruction count times the cache misses per instruction, or the average number of cache misses per instruction. And again, you can write that in terms of the miss rate. So the number of cache misses per instruction will be equal to the average number of memory accesses per instruction times the miss rate. Okay, so we can use this formula for this particular question. So has anybody worked this out? What would the total execution time be with the cache misses? And you can express it in terms of cycles if you like. Anybody worked out what the total execution time would be? Sorry? How do you get that? Okay, I didn't see. Okay.
Oh, Englishman.
Her teachers,
Okay, so putting into the formula, we don't know what the instruction count is, but it doesn't matter because we're just trying to find a ratio. So we have the instruction count times the memory accesses per instruction. So for each instruction, we have to access the instruction itself, and we're told that 40% of the data accesses, 40% is the data accesses, the load and, okay, 40% of the total number of instructions are data accesses, the load and store instructions. Okay, so on average then, an instruction will take, we have one instruction for the instruction fetch and 0.4 as the average number of memory accesses per instruction. Okay, so the memory accesses per instruction is 1 plus 0.4. And then we have the miss rate. We're told the miss rate is 5%, so that's 0.05. And then we have the miss penalty, which we're told is 25 clock cycles. So altogether we have the instruction count times 1.4 times 0.05 times 25, which comes out to be 1.75 times the instruction count. Okay? Do you understand where this 1.1 plus 0.4 comes from? Okay, every instruction we have to fetch the instruction itself, which could result in a data miss. And also for each instruction, 40% of the instructions are load and store data accesses, which again, we could have a data miss. Suppose everything was in cache. Suppose there were no cache misses. How many cycles would it take to execute this program? 1. Not really, because if the data it says if all the memory accesses are cache hits, then the cycles per instruction is just 1.0. Okay, so if everything is in cache, we can assume that it just takes 1 cycle per instruction. Okay, so I haven't quite got there yet. So this is the number of memory store cycles. So if you want to work out the total execution time, then you have to take the CPU clock cycles plus the memory store cycles. So the CPU clock cycles it takes to execute the program is just equal to the instruction count, because it's the CPI is 1, and the memory store cycles is 1.75 IC. So the execution time in terms of cycles is the instruction count plus 1.75 times the instruction count, which is 2.75.
Do we assume clock cycle time will be 1?
Okay, it doesn't really matter, because we're going to have we're just going to calculate the ratio anyway, so it doesn't really matter what the clock cycle time is. So actually, I mean, here I'm just calculating the execution time in terms of cycles rather than seconds, but it doesn't matter because we just want the speed up. Yeah. Okay, if we don't have any cache misses, then the instruction time in terms of clock cycles will just be equal to the instruction count. So if we had no cache misses, our program would execute 2.75 times faster. Okay, any questions on that?
Battery low.
Okay.
Okay, so to go on to the next part of the question then. For the next part of the question, it's slightly different. Here we're told to assume that the CPI is 2. So when all of the memory accesses are cache hits, it will take 2 cycles per instruction. And now we're also supposed, also suppose that we have a miss rate of 2% instead of 5%, but other factors are the same. So we're asked, with a CPI of 2.0 and a miss rate of 2%, will this computer go faster or slower than in the previous example? Okay, so we can use the same formula as before. So again, using the same formula as before, the memory stall cycles is equal to the instruction count times the memory accesses per instruction times the miss rate, and then we have to multiply by the miss penalty. So how many memory store cycles will we have in this example? Somebody work it out? Point. The number of memory access, what's the number of memory accesses per instruction?
2.
Sorry? 0.7, okay. Yeah, 0.7. Okay, so we use the same formula as before. So again, the number of memory accesses per instruction will be the same because we have one access for the instruction and 40% of the instructions access data. Okay, so the average number of memory accesses per instruction is 1 plus 0.4. Now we have a miss rate of 2%, so it's 0.02 rather than 5%. And now the memory stall cycles, the miss penalty, again 25. So multiplying this out, we have 1.4 times 0.02 times 25, which comes out to be 0.7 times the instruction count. So for the CPU clock cycles, it's the instruction count times the CPI, and the CPI is 2, and then we add on the memory stall cycles, which is 0.7, so altogether we've got 2 plus 0.7, which is 2.7 times the instruction count. So we're asked to compare this with the previous example, where we had a computer which operated at 1 CPI, but we had a cache miss of 5%. Does this go faster or slower?
Slow.
Slightly faster. By how much?
0.05. 0.05.
1 point.
Yeah.
2 point. How much faster?
Comparison.
What's the ratio?
Slower, right? Just now was 2.75.
Yeah, before it's 2.75.
Now it's 2.75.
Yes. So which is better?
Yes. This is better.
A smaller execution time is better. Okay? So this has an execution time of 2.7 times the instruction count. The other has an execution time of 2.75.
So this is
times
better.
the instruction count. there's a small improvement, so this will go slightly faster. Okay, the ratio is 2.75 over 2.7, which is 1.02. So again, you're asked to draw some conclusions. So what can we say? What can we say in this case? What conclusions can we draw?
Your cache may not improve the CPU processing capacity.
Yeah.
Even though the CPU itself is slow.
Yeah. Okay. So I think the point the question is trying to make here is that although in B the computer is slower, because this computer takes 2 cycles per instruction, whereas the first computer takes just 1 cycle per instruction. So this computer, in terms of cycles per instruction, is slower, but in fact we get better performance because we have a smaller cache miss. Okay, we only have a cache miss of 2% rather than 5%. So this says something about how to design a computer. A designer could spend a lot of time trying to improve the number of cycles per instruction, or try to reduce the number of cycles per instruction. A designer could spend a lot of time trying to make the computer more efficient in terms of cycles per instruction, but if there's not enough cache memory, then even if you improve the cycles per instruction, you may get a poorer performance if you don't have enough cache memory. Okay, so the design of cache memory is very important to the performance of the computer. Okay, so that's question number 2. Any questions on question number 2? Okay, so the last question talks about different ways of mapping the main memory into the cache memory. So we're told that we have a cache memory of 512 bytes altogether, and it's divided up into blocks of 64 bytes. And we have a main memory of 2 kilobytes, and we're asked to draw some diagrams showing how the memory blocks are mapped into the cache. And here we have 3 different ways we can do this, called direct match, and 4-way or n-way set associative mapping, and fully associative. Okay, so let's work it out first in terms of blocks.